Berlin, late November, 1939. The air in the Reich Ministry of Economics laboratory was thick with the faint acidic scent of coal tar and the rhythmic, comforting hum of vacuum pumps, a sound Dr. Ernst Fenning had long associated with the future. The room was not large, nor was it brightly lit. Every piece of glassware, every etched measuring line, every drop of reagent spoke to a national commitment to precision, efficiency, and above all, parsimony. Fenning, a man whose hands were stained permanently ochre from working with aromatic compounds, watched as the last pale yellow distillate dripped into his flask. It was the latest, most refined product of the Fischer-Tropsch synthesis, fuel, born not from the geologic luxury of buried crude, but from the intellect and sheer grinding labor of the German chemical complex. He held the flask up to the single focused electric lamp, and a thin, satisfied smile touched his lips. It was fuel for the Luftwaffe, engineered molecule by engineered molecule from lignite coal and the forced marriage of hydrogen and carbon monoxide, a testament to German ingenuity rising above the biological accident of geography. He knew the Americans possessed the black, oily abundance beneath their plains, the sheer, staggering, lazy volume of it. But their methods, their crude cracking and refining, lacked the scientific elegance and the absolute, calculated necessity that drove the German war machine. Fenning chuckled, a low, dismissive sound that echoed lightly off the steel workbench, thinking of the American technical reports that filtered through intelligence channels, reports that spoke of simple, raw material-dependent industries that could only succeed through sheer volume. Such an approach, Fenning believed, was the ultimate mark of an unevolved nation, one that prioritized tonnage over topology. This, Fenning believed, was the core difference. Germany was engaged in a war of complex chemistry and engineering, while the Allies were preparing for a mere war of logistics and accounting. The entire German strategy, from the sleek lines of the Messerschmitt Bf 109 to the complex metallurgy of the 8.8 centimeter flak gun, was predicated upon solving the crushing problem of resource scarcity through superior, smarter technical design. They could not simply pour fuel into the engines. They had to create the very concept of fuel from earth and air. This constant, relentless drive for energy density, getting the maximum kinetic output from the minimum required volume, was, in Fenning's mind, the ultimate metric of military power. The fuel he had synthesized in his small, precise flask was a triumph of the will over geological fate, a concentrated, high-octane solution to a problem the Americans had never even had to consider. They simply opened a valve. This philosophical and technical gulf was, Fenning was certain, an unbridgeable advantage. The American P-40 Warhawk was a big, heavy, dependable machine, but it was, fundamentally, a product of a brute force economy, designed with the casual contempt for efficiency that only unlimited petroleum reserves could foster. When Germany's fuel tanks were nearly empty, they relied on chemists like Fenning to invent new ways to run on air and dust. When the American tanks were empty, they just called a different oil company. It was a difference not of scale, but of fundamental character, of national technological ethos. But that sheer, terrifying scale was precisely the lurking shadow that Fenning and his colleagues consistently minimized. The mathematics of abundance operate under an entirely different set of rules than the mathematics of scarcity, and no amount of elegant chemical engineering could negate the cold, brutal geometry of the production numbers. In that same month of November, 1939, the Reich's industrial capacity allowed for the production and synthesis of liquid fuel, crude and artificial combined, at a daily rate that rarely exceeded 70,000 barrels, a figure stretched taut across the entire military and civilian economy. It was a remarkable feat of synthetic chemistry, a powerful testament to the barbaric precision of their engineering. Yet, on the other side of the Atlantic, in the sprawling, often haphazard fields of Texas and Oklahoma, the wells of the United States were already gushing forth at a rate that surpassed 3,500,000 barrels of crude oil per day. The contrast was not one of ingenuity versus waste, as Fenning believed. It was the overwhelming, unyielding power of the statistical reveal. The German genius was forced to achieve 95% efficiency on 1 unit of resource, while the American genius could afford to achieve 50% efficiency on 100 units. When the two forces inevitably met, the resulting conflict would not be determined by the purity of the synthetic distillate, but by the sheer tonnage of hydrocarbon energy that could be delivered to the front lines. The difference between 70,000 and 3,500,000 was not merely a logistics problem, but an unapologetic military history waiting to be written in fire and steel, a grim ledger that would ultimately catalog the failure of ingenious scarcity against the avalanche of material abundance. Fenning's chuckle was the sound of a man who had won the chemistry test, but who was tragically unaware he had failed the final examination in industrial supremacy. Cambridge, Massachusetts, early 1942. While the meticulous, calculating chemists of the Reich were desperately engineering every molecule from coal dust, the American answer was taking shape, not in a cavernous, state-sponsored industrial complex, but in the quiet, ivy-covered confines of Harvard University. Here, in a laboratory devoted more to the elegant structures of organic chemistry than the grim calculus of modern warfare, worked Dr. Louis Fieser, a man whose professional life was a study in pure, unhurried academic curiosity. Fieser was no dramatic figure of military science. He was unassuming, precise, and dedicated to the subtle art of synthesis, the intellectual challenge of building new, previously unknown molecules. His world was the six-sided symmetry of the benzene ring and the esoteric properties of quinones, not the brutal pragmatic demands of ordnance and destruction. Yet it was here, in this sanctuary of peacetime science, that the ultimate chemical expression of American industrial abundance would be unknowingly conceived, a direct and devastating counterpoint to Dr. Fenning's desperate European ingenuity. The prevailing Allied doctrine, forged in the merciless trenches of the previous global conflict and hardened by the initial setbacks of World War II, was simple, kinetic, and overwhelming. The solution to every tactical problem was high explosive. The military mind, with its preference for quantifiable results, worshipped the mathematics of kinetic energy and shrapnel. A bomb was a hammer, and the enemy was a nail. The faster and harder the hammer blow, the better. TNT, RDX, Composition C. These were the gods of the battlefield, chemicals that specialized in instantaneous, visceral transformation, turning structure into debris and life into fragmentation wounds within a fraction of a second. This commitment was not merely strategic, it was almost religious. The American war machine was pouring billions of dollars and millions of man-hours into optimizing the shape of a blast wave, the density of a projectile, and the yield of a crystalline compound. Fire, by contrast, was viewed as secondary, a messy, unpredictable byproduct of the true weapon. It required oxygen, it required time, and it required a degree of logistical complexity that seemed unnecessary when 1,000 pounds of high explosive could simply obliterate the target outright. When Fieser was first approached by the National Defense Research Committee, the task they gave him seemed almost trivial in the grand scheme of the war effort: find a better way to gel gasoline. The existing method, which involved crude mixes of natural rubber, was unstable, unreliable, and consumed a strategic material, rubber, that was rapidly becoming scarce due to the conflict in the Pacific. Fieser, approaching the problem with the intellectual curiosity of a man solving a complex puzzle, set aside the urgency of war to focus on the stability of the colloid. The materials he used were humble: simple salts, readily available fatty acids, and the endless stream of petroleum products that flowed unimpeded from the American heartland. His initial success, a stable, cohesive jelly that could hold gasoline in suspension, was presented to the ordnance experts as a scientific curiosity, a chemical novelty that seemed to have no immediate, devastating application. It was, in the immediate context of optimizing TNT yield, a worthless gel, a technical distraction from the serious work of mass-producing the pure, unadulterated power of detonation. The contempt in the eyes of the Army brass was palpable. They demanded solutions that were fast, final, and fragmenting. Their mission was to drop hammers from heaven, not to set slow, messy torches upon the enemy. One high-ranking Army ordnance officer, reviewing Fieser's report in the early summer of 1942, reportedly dismissed the idea with cold finality, a quote that perfectly encapsulated the prevailing mindset. "We need hammers from heaven, not torches." They failed to grasp the central ironic truth of Fieser's work, that by solving a problem of material science, how to make liquid fuel adhere, he was creating a weapon that possessed the one quality high explosive lacked: statistical efficiency in area denial. High explosive relied on pinpoint accuracy and the ephemeral physics of the blast wave. Fieser's simple, humble gel, which he would christen napalm, did not. It adhered, sustained, and spread, turning fire from an accidental consequence into a devastating engineered primary weapon, a tool that would ultimately prove more effective at reducing the enemy's industrial and civilian infrastructure than any amount of pure kinetic energy. The most destructive weapon of the later war was born not of the urgency of scarcity, but of the unassuming academic's attempt to stabilize a simple jelly. A quiet experiment in chemistry driven by curiosity, soon to be amplified by the overwhelming, unquestioning power of American industrial abundance. Tunisia, the arid, unforgiving expanse of North Africa, early March, 1943. The dust was not merely a feature of the landscape, it was an actor in the drama, a blinding, choking, omnipresent force that elevated the chaos of battle into a nightmare of sensory deprivation. At 700 hours, Lieutenant Wallace, Wally Denton, piloting his low-slung P-39 Airacobra, descended through the early morning glare with orders to interdict a German armored column moving through the narrow passes near Kasserine. Denton was not armed with the hammers from heaven, the heavy-caliber, high-explosive ordnance his commanders preferred, but with a pair of crude, jetisonable wing tanks filled not with aviation fuel, but with a jellied mixture of gasoline, the most rudimentary form of an incendiary munition. The intent was strategic: to light up the battlefield, to blind the enemy, and to induce panic among the tank crews and supporting infantry, transforming their supply vehicles into pyres. The reality, however, was a devastating, farcical display of technical failure. Denton lined up his pass, the crosshairs steady on the lead Panzer III, and toggled the release. The twin tanks dropped away, aerodynamic shells designed for one purpose, now tasked with another, and the whoosh of their descent was followed by two heavy, hollow thunks as they struck the sand short of the target. They ruptured as designed, but the effect was immediate, spectacular, and utterly useless. A massive, blossoming orange fireball erupted, throwing a blinding heat over a 300-foot radius, a visceral sheet of thermal energy. The lead tank was engulfed, but only for a moment. Pure gasoline, even crudely thickened, burns with the reckless speed of a flash fire. It consumes its own volatile vapors almost instantly. Within 6 seconds, the flame had collapsed inward, leaving behind a dark, oily patch of burning residue, easily avoided by the following tanks, which simply skirted the scorched earth and continued their advance. The enemy infantry, caught initially by surprise, did not flee in panic, but merely adjusted their formation, their laughter reportedly filtering back to Allied intelligence reports. "They are just dropping hot water," one German officer was said to have quipped. This brief, devastating failure encapsulated the entire problem of early incendiary warfare, The catastrophic, yet statistically inefficient, burn. The gasoline was not adhering, it was not sustaining, it was simply scattering the fire rather than concentrating it. The initial attempts to create a sticky fuel had relied on mixing standard aviation gasoline with a meager supply of natural rubber, an absurdly logistically demanding compound in a war where the Japanese had severed the supply chains to the rubber plantations of Southeast Asia. This rubber-thickened fuel, known variously and disparagingly by the ground troops as goop, or more memorably, flying milk bottles, was an absolute nightmare. The compound was heavy, consuming precious payload capacity. It was unstable, degrading rapidly in the heat of the North African sun, and critically, it failed to deliver a truly devastating thermal assault. The fire it created was either too volatile, flashing out before structural damage could be inflicted, or too viscous and heavy, simply falling in a clumpy mass that allowed the enemy time to react and suppress the burn. A detailed logistical analysis from the Allied supply depots revealed the grim truth. The transport burden for these early systems was crushing, requiring enormous quantities of precious fuel and stabilizing agents for minimal transient tactical effect. The statistical reveal was damning. The rate of structure-to-structure fire spread, the true measure of a successful incendiary weapon, was dismally low, often less than 10%. Fire, to be effective, must act as a self-propagating agent of destruction, jumping from vehicle to vehicle or house to house, creating a firestorm that denies territory and destroys infrastructure through cascading, overwhelming thermal force. The early crude gels failed this basic engineering requirement. They created spectacular, yet isolated, individual fires that were logistically expensive to deliver and easy to suppress. The high-explosive ordnance, while costly in materials, delivered a final, undeniable kinetic result. The incendiaries delivered a brief, terrifying light show, followed by a tactical zero. The realization crystallized among the few forward-thinking scientists and tacticians. The solution did not lie in finding a better way to start a fire, but a better way to make that fire adhere and sustain. The hammer was fine, but they needed a liquid, adhering torch that could not be shaken off or smothered, a chemical formulation that would elevate fire from an unpredictable byproduct into the ultimate, unapologetic military tool of territory denial and industrial destruction. The war could not be won with flying milk bottles. Harvard University, late summer 1942. The atmosphere within Dr. Louis Fieser's laboratory was now subtly different. The task, initially dismissed as a trifling academic distraction by the purveyors of kinetic destruction, had become a focused, dedicated pursuit. It was not the urgency of the war that drove Fieser, but the elegant, uncompromising logic of chemistry. If the existing rubber-based mixtures failed because the thickening agent consumed a strategic resource and the resulting gel was unstable, the solution must lie in abundance and stability. He required a material that could be produced in limitless quantities, that was industrially trivial, and whose resulting compound was utterly reliable, unaffected by heat, shock, or the corrosive nature of the petroleum it was intended to contain. The answer, when it came, was a triumph of elemental simplicity, a chemical breakthrough born of the United States' immense, unappreciated wealth in basic industrial feedstocks. The successful formulation was found not in a complex, multi-stage synthesis of rare German ingenuity, but in the straightforward combination of two readily available, almost offensively common materials, aluminum naphthenate and aluminum palmitate. Naphthenic acid, a cheap and voluminous byproduct of the petroleum refining process itself, was a material so abundant it was practically being discarded. Palmitic acid was derived from the immense agricultural output of the American heartland, the fatty acids of common soap production. It was, in effect, a weapon forged from industrial waste and cooking grease, an ultimate expression of unlimited resources applied to a tactical problem. The reaction was almost anticlimactic in its ease. A mere blending of these aluminum salts of fatty acids with the standard aviation-grade gasoline, a gentle stirring until the transformation was complete. It was a reaction requiring no specialized equipment, no hyper-precise temperatures, and no exotic catalysts. The kind of process that could be scaled up from a beaker to a 4,000-gallon mixing vat without altering the fundamental chemistry. Fieser watched the transformation with the quiet satisfaction of a true scientist. In the glass beaker, the clear, volatile gasoline, which typically burns with an ephemeral, scattering fury, was being transmuted into something entirely new. It had become a thick, translucent, golden brown jelly, holding the explosive potential of the fuel hostage within its simple, three-dimensional mesh. The juxtaposition of scales was immense. Here, in the small glass confines of a laboratory, a process of molecular entanglement was occurring, the aluminum salts forming a complex scaffolding that trapped the liquid hydrocarbon, and yet this microscopic, almost beautiful chemical reaction would ultimately unleash unimaginable devastation on a continental scale. This unassuming jelly was the answer to the tactical failure of the flying milk bottles, the solution to the problem of adherence and sustenance. The secret lay in the material's unique, terrifying physical property, known to chemists as thixotropy. The gel was, paradoxically, a solid when at rest, but a liquid when agitated, stressed, or subjected to intense mechanical force, such as the impact of a drop tank hitting a concrete structure. It behaved like a molecular net. Upon impact, the gel would briefly liquefy, allowing it to splash and spread rapidly, adhering to whatever surface it encountered with terrifying tenacity: concrete, steel, brick, and flesh. Crucially, as the mechanical stress subsided, the mesh would instantly reform, turning the flammable liquid back into a semi-solid state that resisted flow and self-extinguished. The fire, once ignited, would be trapped against the target, burning until the last molecule of gasoline was consumed. This was the narrative-driven technical deep dive. The fire was no longer a flash, it was an adhering, self-sustaining furnace. Where the high explosive sought to pulverize through kinetic shock, this gel sought to consume through time-released, relentless thermal energy. It made the fire an inescapable component of the target. It was this very molecular structure, the naphthenate and the palmitate, that gave the compound its instantly recognizable and soon-to-be universally feared name: napalm. The word itself possessed a clean, chilling finality, a single, two-syllable declaration of total thermal war. Fieser's work had transcended the simple military requirement of a reliable thickening agent. He had inadvertently delivered the final, most devastating expression of the American industrial ethos. It was a weapon of simple, mass-producible chemistry derived from limitless resources, possessing a physical property that made its destructive power exponential. The emotional tone was one of awe-inspiring realization. The complex, brittle genius of German synthetic chemistry was about to be met and decisively overwhelmed by the simple, abundant, and utterly lethal elegance of Fieser's sticky gel. The chemists had done their job. Now the engineers and the factories would begin the relentless, horrifying work of turning this small beaker of golden brown jelly into an avalanche of steel and lead. The laboratory door at Harvard had barely closed behind Dr. Louis Fieser before the enormous, utterly uncompromising industrial engine of the United States roared to life. The chemical breakthrough, so simple and so profoundly effective, required no further theoretical contemplation. It simply demanded application, and application was what American industry delivered with the force of an avalanche of steel and lead. The transition from a few ounces of glistening, golden brown gel in a beaker to a flood of product measured in millions of pounds was instantaneous, a testament to the nation's unquestioning faith in scale. The problem of war for the Americans was rapidly devolving from a question of how to fight to a problem of how much could be manufactured, and napalm, born of unlimited resources, was the ultimate answer. Across the continent, in newly constructed, often purpose-built factories, vast pristine edifices of concrete and glass, fully electric lit and operating 24 hours a day, the simple formula of aluminum naphthenate and aluminum palmitate was translated into an industrial dogma. There was no bottleneck, no need for the painstaking, low-yield engineering of the German chemists. Dr. Pfennig's Fischer-Tropsch plants in the Reich were complex, multi-stage nightmares of high pressure and high heat, desperately squeezing precious, complex molecules of fuel from coal dust, a triumph of technical elegance, but one easily shattered by a single, high-explosive strike. Their process was a fragile, high-maintenance pyramid of chemical wizardry, yielding ounces for every pound of input. The American napalm line, by contrast, was a model of unlimited throughput. Its ingredients, industrial-grade fatty acids, and the abundant waste products of the massive petroleum industry, flowed in a continuous, uninterrupted torrent. The sheer, overwhelming simplicity of the chemistry meant that the production process was almost crude. Colossal mixing vats, simple agitation, and continuous flow filling machines. It was a factory process that celebrated volume over refinement. The command from the Army Chemical Warfare Service to industry was absolute and relentless. Produce at any cost, and produce more than any rational analysis suggested was necessary. The initial production quotas of mere thousands of pounds per month were instantly rendered irrelevant, replaced by demands for hundreds of thousands, then millions. The concept of industrial capacity was not just a term of economics, it was the ultimate deciding military weapon, and it was brought to bear with unbridled ferocity. The nation's immense petroleum reserves, the subject of Dr. Pfennig's earlier dismissive laughter, now provided not only the essential aviation fuel to be thickened, but the very chemical precursors that made the gel possible. It was a closed-loop system of self-amplifying destruction, an Ouroboros of fire and oil. This scale was deliberately and ruthlessly employed as a counterpoint to the enemy's scarcity. While the Luftwaffe was forced to ration its synthetic fuel, conserving every precious liter of its high-tech distillate, the American military was preparing to deploy millions of gallons of a substance derived from materials so cheap they were considered waste. The sheer, unlimited resources of the United States meant the weapon could be manufactured, stockpiled, and ultimately wasted in a manner utterly incomprehensible to a resource-constrained nation. Where the German war effort was a meticulous ledger of input versus output, the American effort was an open checkbook backed by a bottomless well of raw materials. This was the true genius of napalm's industrialization. It converted the American economy's commodity abundance into military superiority. The resulting production landscape was a visually stunning contrast. In Europe and Asia, the war was a spectacle of rubble and bomb damage, industry reduced to skeletal remains and scattered dust, the result of scarcity fighting against the odds. But in the States, the vast new chemical plants stood pristine and perfect, humming with the continuous power of 24-hour production. These were not factories struggling to maintain output, but industrial organisms effortlessly exceeding every quota, preparing to unleash a continuous thermal assault. The material produced, the stable, sticky napalm, was poured into millions of metal canisters and vast newly designed fuel delivery tanks, transforming the entire logistics chain into a single, massive delivery system for adhering fire. The repetition of this capacity became the mantra of the Allied command. More ships, more planes, more fuel, and always millions more pounds of the chemical gel. This was not a weapon invented on the drawing board. It was a force of nature. The industrial engine awakened, preparing to prove with unforgiving statistics that the complex chemistry of scarcity was no match for the simple, overwhelming physics of unlimited industrial capacity. Pforzheim, Germany, late February 1945. The American air fortress, the Iron Maiden, a B-17 flying fortress, was a tiny, thunderous speck suspended in the cold, thin air 5 miles above the continent. Sergeant Michael "Mickey" O'Malley, the bombardier, had a view that stretched from the pale, distant horizon to the patchwork of darkness below. His mission on this night was distinct from the hundreds before it. His bay doors were not filled with the familiar high-density eggs of general-purpose, high-explosive, but with clusters of the new M69 incendiary, hundreds of small, streamlined metal canisters, each a precise, compact delivery system for Dr. Fieser's adhering gel. The moment was the climax at the midpoint of the industrial war, the instant the statistical genius of unlimited resources met the human reality of a German city. The German defenses below, practiced and hardened by years of aerial siege, watched the bombers with grim, professional resignation. Down on the ground, Gunther Hess, a 19-year-old former Fallschirmjäger now manning a searchlight battery, watched the distant drone of the formation. They expected the usual hammers from heaven, the shattering concussion of TNT, the kinetic shock that reduced stone to dust. Hess, like his comrades, had learned the drill. Survive the blast wave, then fight the immediate, manageable fires started by conventional phosphorus and magnesium incendiaries. The American bombs, he knew from intelligence, were predictable. They struck, they exploded, and the moment passed. As the Iron Maiden reached its release point, O'Malley toggled the selector, his final action a dispassionate calculation of wind drift and air speed, and the M69 clusters tumbled silently toward the dark, unsuspecting city. When the cluster bombs separated and the individual M69 canisters began to impact, there was no massive defining thunderclap of a high-explosive blast. Instead, the night was split by a multitude of sharp, tearing sounds, like a giant sheet being ripped. Hess, watching from his bunker, initially scoffed. "They are just dropping gasoline," he shouted to a nearby comrade, the derision heavy in his voice, recalling the earlier, inefficient incendiaries of the North African campaign. The first fires that blossomed were not the ephemeral, flashing spheres of pure gasoline, but something fundamentally, terrifyingly different. The napalm, released from its casing by a small burster charge, did not scatter. It seemed to pour itself onto the target surfaces, adhering with an unnatural, glue-like tenacity. Where a conventional bomb would strike and dissipate its energy outward, the M69 seemed to focus its thermal energy inward, turning the air into a slow, sustained oven. The fire did not flash out. It sustained and consumed. It ran down the walls of buildings, clinging to the brick and wood, ignoring the attempts of civilian fire crews to suppress it with water. Water merely spread the burning, floating gel, turning the firemen's hoses into vectors of destruction. The light was blinding, but the heat was a palpable, crushing physical force. Hess watched in growing terror as the initial isolated fires did not remain isolated. The simple, elegant chemistry of the thixotropic gel meant that the fire spread rate in the target area was not merely increased, but tripled compared to any previous raid. The sustained thermal output rapidly preheated neighboring structures, creating a self-amplifying, catastrophic conflagration that fused into a single, rolling firestorm. The American command had discovered, not a new bomb, but a new tactical weapon: area denial by sustained thermal annihilation. The statistical reveal of the raid was the cold, unfeeling proof of Fieser's chemical superiority: a single 500-pound cluster. Bomb, laden with the adhering gel, possessed the destructive capacity, in terms of structures destroyed and area rendered uninhabitable, of an entire stick of conventional 1,000-pound general-purpose, high-explosive. The equation of warfare had been fundamentally rewritten. The industrial power of the United States had not merely produced more weapons. It had produced a weapon whose simplicity and scale turned the very process of combustion into a strategic instrument of unparalleled efficiency. Gunther Hess, scrambling now not to fight the flames but to escape them, knew with a certainty that transcended military training that this was not merely a heavier hammer. It was an inescapable, unrelenting flood of adhering fire, a terrifying, visceral demonstration that the era of complex, brittle scarcity was now being consumed by the simple, overwhelming thermal mathematics of unlimited American abundance. The smoke had barely cleared from the wreckage of Pforzheim before the American military command recognized that the M69 incendiary bomb, with its lethal payload of Dr. Fieser's adhering gel, was not an incremental improvement to the ordnance inventory. It was a fundamental chemical re-engineering of the battlefield. The initial reports detailing the sustained, unmanageable nature of the fires and the shocking efficiency in destroying civilian and industrial infrastructure instantly invalidated decades of high-explosive doctrine. Napalm was not a weapon in the traditional sense of a projectile designed for kinetic impact. It was an industrial tool for landscape-scale destruction, a devastating realization that quickly and coldly rewrote the entire tactical manual for both air and ground forces. The strategic shift was rapid and brutal. If the B-17s could use it to destroy cities from high altitude, then low-flying fighter bombers could use it to sanitize the immediate tactical landscape, clearing out fortifications, gun emplacements, and entrenched infantry with an efficiency no high-explosive round could ever match. The key lay in the technical deep dive of its delivery system. The dedicated M69 cluster was effective, but the American industrial capacity offered an even more abundant, easily disposable vehicle, the external fuel drop tank. Originally designed to extend the operational range of fighter aircraft like the P-47 Thunderbolt and the P-51 Mustang, these sleek, belly-slung tanks were simply fuel containers, products of the same unlimited resources that had birthed napalm itself. They were cheap, mass-produced, and, most critically, designed to be dropped when empty or no longer needed. This disposable fuel tank, once filled with the dense, sticky gel, became the ultimate napalm delivery vehicle. A fighter aircraft already armed with 6 or 8 50 caliber machine guns and the terrifying muzzle energy of 2,500 pounds per minute of lead was instantly transformed into a flying flamethrower. The process of dropping the tank and igniting the fuel upon impact was simple, reliable, and utterly devastating. The pilot was no longer flying a vehicle for ammunition, kinetic energy that had to be aimed with precision, but had effectively strapped himself to a locomotive of pure thermal energy, capable of spraying a 100-gallon curtain of sustained fire over an area hundreds of feet long. This was the true genius of the industrial adaptation, taking a non-weapon component, the fuel container, and converting it into a large-scale, tactical incendiary delivery system, a fusion of logistics and firepower that the resource-starved Reich could never replicate. The strategic consequences were laid out with cold clarity in the diary of Major General Harmon W. Hub Rice, an Allied logistics commander who oversaw the integration of the weapon into ground support doctrine. 23 March 1945. The numbers are conclusive. An infantry squad requires 67 pounds of high explosive and 20 minutes of close quarters fighting to clear a well-constructed bunker. The same bunker, subjected to 110 gallons of the new gel from a single P-47 pass, is neutralized in 90 seconds with 0% casualty risk to our troops. The enemy either burns or is denied the space. This is not war, it is industrial output meeting human resistance. We are no longer calculating a human cost-to-kill ratio. We are calculating the human cost to industrial output ratio, and the output ratio overwhelmingly favors the continued, massive deployment of this fuel. It is the most efficient expenditure of crude oil in history. Rice's stark assessment revealed the chilling core of the strategic shift. Napalm was an exercise in unapologetic military business history. It eliminated the variables of individual valor and complex maneuver by replacing them with a reliable, predictable outcome of mass thermal destruction. The battlefield was now a chemical equation where the variable of adhering fire guaranteed the rapid neutralization of resistance, turning previously entrenched, time-consuming defensive positions into areas of instant, absolute denial. The fighter aircraft, once an instrument of kinetic dogfight and precise bombing, became a mechanism for spreading adhering fire, delivering a volume of destructive power that made a mockery of German defensive engineering. This new reality meant that the industrial might of the Allies was now, quite literally, coating the European continent in a thick, sticky layer of self-sustaining fire, fundamentally altering the very calculus of survival for the soldiers and civilians on the ground. The simple gel, conceived in academic curiosity, had become the ultimate expression of technical industrial supremacy narrative. Iwo Jima, February 1945. The change of theaters from the bomb-scarred concrete of the Reich to the volcanic ash and coral of the Pacific Islands did nothing to diminish the brutal efficacy of the adhering gel. In fact, the weapon found its ultimate, most terrifying purpose against an enemy whose entire military doctrine was predicated on the absolute defense of ground. The Japanese military, bound by the Shōwa doctrine of unyielding resistance, had perfected the art of defensive warfare, transforming the islands into layered subterranean fortresses. Their strength lay in deep, interconnected networks of bunkers, caves, and pillboxes, positions where high explosive, the worshipped hammer of the earlier war, proved stubbornly inefficient. High explosive struck the surface, shattered rock and soil, but the blast wave dissipated, leaving the defenders deep within their earthworks, shaken but ready to fight on. It was a tactical stalemate, a brutal war of attrition measured in ounces of lead and gallons of blood. The introduction of napalm changed the equation from one of kinetic force to one of absolute thermal saturation. The American military was not interested in physically crushing the Japanese defenses. It was intent on consuming them. The new weapon, delivered not just by low-flying P-38 Lightnings, but by ground support tanks equipped with flamethrowers carrying the now ubiquitous gel, offered a terrifying ability to bypass these multi-layered defenses, not through superior penetration, but through overwhelming adhering heat. The Japanese bunkers, designed to withstand the crushing percussion of a 1,000-pound bomb, were utterly defenseless against a liquid that could pour through a ventilation slit, a firing aperture, or the smallest crack in the concrete, and then transform into a self-sustaining furnace. Sergeant Kenji Tanaka, a machine gunner on Okinawa, experienced the deployment firsthand. His position, a painstakingly constructed cave complex, fortified with 8 feet of reinforced coral and steel, was a testament to the brutal efficiency of Japanese military engineering. They had endured days of relentless shelling. The earth shook, rock crumbled, but they held the line. Then came the sound that was not a crack or a boom, but a soft, wet splat followed by a sudden, intense light. The sticky, golden-brown substance did not explode outside. It flowed into the main firing slit, adhering instantly to the metal and concrete. The air, which moments before was cool and breathable, became thick, acrid, and instantly lethal. The fire, fed by its own relentless chemistry, sustained and consumed the oxygen with a speed that turned the cavern into a suffocating oven. Tanaka did not die from a shell or a bullet. He was defeated by the simple, undeniable physics of fire trapped in an enclosed space. The heat was so intense it warped the steel of his machine gun and fused the sand to the wall, a monument to the power of the adhering gel. This was the final devastating chapter in the mathematics of defeat. The U.S. command watched the casualty. Numbers and the bunker clearance rates plummet dramatically with the introduction of this new weapon. Where days of brutal hand-to-hand fighting were once required to root out a single entrenched position, a single, properly delivered napalm strike could neutralize the position in minutes. The logistical nightmare of clearing complex fortifications was reduced to a simple equation of thermal saturation. It proved once and for all that against an enemy committed to total resistance and utilizing finite resources for deep static defenses, the American strategy of unlimited resources and unapologetic technological supremacy was an unanswerable force. The ability to deploy millions of gallons of a substance that defied cover and consumed oxygen meant that the strategic geography of the Pacific, the endless supply of subterranean strongpoints, was suddenly rendered irrelevant. The war in the Pacific was transformed from a slow, grinding slugfest into a chilling, somber acknowledgment of inevitable defeat, brought not by superior manpower, but by the devastating chemical finality of a sticky, man-made hell. The Japanese knew how to fight the man and the bullet, but no amount of iron will could defeat the chemical simplicity of adhering, consuming fire. The guns fell silent, the fires were eventually choked out, and the immense, terrifying curtain of smoke that had hung over the globe began slowly, fitfully to dissipate. Yet the end of World War II did not bring an end to the consequences of the adhering gel. Instead, it opened a new, profound chapter in the moral calculus of modern warfare, one where the final decisive factor was determined not by ethical consideration, but by the cold, unquestioning power of industrial capacity. The proponents of the weapon argued with unassailable logic that napalm had been an essential tool for ending the conflict sooner, saving the lives of tens of thousands of Allied soldiers who would otherwise have been consumed by the brutal calculus of island hopping or the grinding fight across the European plain. It was a utilitarian argument, a brutal cost-benefit analysis where American lives were placed on one side of the ledger, and the wholesale thermal annihilation of the enemy's societal and industrial fabric was placed on the other. This was the profound irony woven into the very fabric of the weapon's creation. The nation of unlimited resources, the land of plenty, had harnessed its astonishing abundance, not to create more food or more consumer goods, but to design a device whose primary purpose was waste, the complete, instantaneous incineration of an adversary's industry and the human infrastructure that supported it. The industrial-grade fatty acids and the throwaway byproducts of the petroleum stream, materials so trivial they were almost discarded, had been elevated to the most potent tools of strategic destruction. The simplicity of Dr. Fieser's chemistry had done more than just create a sticky fuel. It had fundamentally changed the rules of warfare, making the civilian population, the workers, and the families who supported the axis of industry an undeniable, unavoidable target. When a weapon can pour through the smallest crack and adhere relentlessly to any surface, the old distinction between military installation and residential structure becomes meaningless, transformed by the chemical simplicity of the burning gel. The post-war military doctrine, reviewing the astonishing efficiency rates of the thermal assaults on both German and Japanese cities, cemented this new reality. The lesson was clear. To defeat a modern industrial power, one must destroy its ability to produce, and the most efficient way to achieve that end was not through the blunt kinetic force of the past, but through the pervasive, unrelenting fire of the future. The simple aluminum salts had become the chemical foundation of strategic deterrence. The triumph of the American technical industrial supremacy narrative was complete, but it carried with it a terrifying, unspoken consequence. The realization that the capacity for total war was now directly linked to the capacity for total, area-wide destruction. Decades later, looking back on the consequences of his deceptively simple, elegant discovery, Dr. Louis Fieser, the unassuming Harvard chemist who had merely sought a stable colloid, carried the quiet weight of the world's burning. He had watched his simple, golden-brown gel transition from a laboratory curiosity to the most recognizable symbol of American thermal power, deployed in conflicts long after the initial war had ended. His reflection, a sharp thesis-defining quote that cut through the military rationale and logistical necessity, captured the terrible finality of his contribution. The truth is, it worked too well. It was just gone, transformed into burning debris. It was a statement that acknowledged the pure, relentless efficiency of the chemical process, a scientific success that yielded a human and moral tragedy. The problem was not the formula. The problem was its scale. And that scale, the definitive proof of the American industrial engine's unbridled capacity, was the final, devastating statistical reveal. By the time the Japanese surrender was finalized in August of 1945, the United States military, having satisfied the immediate, overwhelming needs of the active war fronts, had stockpiled an astonishing reserve. The production lines, simple and ceaseless, had created and stored a volume of napalm bombs and gel concentrate that amounted to millions of gallons. This immense unused reserve was the final overwhelming testament to the American way of war. Not fighting with what was available, but fighting with an industrial avalanche that guaranteed victory through sheer, unapologetic volume. The war had been won, not by clever tactics or rare materials, but by a simple chemical formula backed by a relentless, unquestioning factory system whose only limit was the literal horizon of the American continent. The legacy of the GIL was the indelible, somber truth that in modern warfare, the final, most terrifying weapon is not a projectile, but unlimited, industrialized fire. The final analysis of World War II transcends the heroic narratives of individual battles, the brilliant maneuvers of generals, or the sheer courage of the infantry. At its most fundamental, it was an unapologetic military business history, a devastating global conflict decided not by military genius on the battlefield, but by an unbridgeable disparity in industrial capacity, translated into tactical dominance by a seemingly simple, yet cosmically significant, chemical compound. The story of napalm is, therefore, the definitive, data-supported final thesis, proving that technical supremacy, when backed by overwhelming and cavalier material abundance, is the single decisive factor in industrial warfare. This was the unspoken premise of the entire conflict, the fatal flaw in the German High Command's belief that superior engineering, the meticulous, high-pressure, complex synthesis of Fischer-Tropsch fuel, could ever defeat the raw, unfettered power of the American oil fields. Dr. Ernst Pfennig's elegant scarcity was ultimately a fragile theoretical construct, a magnificent, intricate machine built on shifting sands. Dr. Louis Fieser's solution, the sticky golden-brown gel, was crude, simple, and utterly unstoppable, a weapon forged from agricultural waste and petroleum byproduct. The battle was fought between the highly refined, complex molecule and the billions of barrels of raw, unrefined crude oil that served as its inexhaustible feedstock. The American industrial machine, fueled by millions of barrels of crude oil and simple chemistry, proved mathematically superior to the German quest for complex, efficient perfection. The sheer volume of raw, easily convertible material dictated a new physics of destruction. The genius of napalm was that it provided a means to convert this unlimited resource, hydrocarbon energy, into a tactically efficient, adhering weapon on a mass scale never before conceived. The German military was forced to conserve and ration every liter of its hard-won synthetic fuel. The American military could afford to drop, burn, and waste millions of gallons of adhering fire, saturating the landscape until the enemy's will to resist simply evaporated in the heat. It was the ultimate expression of industrial supremacy, the ability not just to destroy a target, but to deny the enemy existence in an entire geographic area through thermal annihilation. The final chilling statistics confirmed the thesis. The American production system, unhindered by resource scarcity, produced in excess of 300,000 aircraft, 85,000 tanks, and perhaps most tellingly, millions of gallons of the chemical gel. This volume, combined with the chemical ingenuity that allowed the fire to adhere and sustain, created a geometric progression of destruction that no amount of human bravery or technological elegance could withstand. Napalm was the ultimate equalizer, transforming the sheer magnitude of American material abundance into an unassailable strategic reality. It rendered the enemy's deepest bunkers useless, their complex logistics irrelevant, and their meticulous high-tech defense systems obsolete. The war concluded, the machinery of production slowed, and the evidence of the great conflict remained scattered across the globe. Vast silent graveyards of American aircraft, thousands upon thousands of P-51 Mustangs and B-17 Flying Fortresses, lay dormant, awaiting the scrapyard, a final testament to the nation's ability to overproduce. The landscape was littered with the hulks of German tanks and the wreckage of factories reduced to ash and rubble. Yet, amidst the colossal kinetic detritus of the war, the shattered steel and twisted armor, lay the true, cosmically significant artifact, the tiny, sealed 5-gallon metal can. This humble container, filled with the simple, golden-brown aluminum salts and gasoline, represented the trivial detail that carried the weight of the war's conclusion. It was not the massive high explosive that won the day, but this chemically simple, infinitely reproducible vessel of adhering fire. The lesson was indelible. World War II was not ultimately a battle of men against men, nor machine against machine, but a battle of industrial systems, where the system backed by unlimited resources and the ability to convert simple chemistry into overwhelming, landscape-scale destruction proved to be the ultimate, final, and unanswerable weapon. The power of abundance always defeats the genius of scarcity.